Welcome to solverfy.
This is the answer to chapter 15, problem number 78 from the Smith Organic Chemistry textbook. And this problem is asking us to consider the chlorination of propane, the free radical chlorination of propane. And we're given a lot of information and asked to draw what the product that we have is. And so the first thing that I did was just draw propane, draw the reaction conditions, and then rewrite some of what we've been given. So the formula of our final product is C3H6Cl2, and we get several pieces of information from that formula. Namely, we are now able to definitively say that we have 6 hydrogens and 2 chlorines. So we know that we've added 2 chlorines to this molecule and lost 2 hydrogens from our starting material. And so the way that I started was I looked at the integrations on the NMR that were given. And there are 2 signals on the NMR, one with an integration of 57 units and one with an integration of 29 units. And so you add them together, that adds up to 86. We know that we have to be accounting for 6 hydrogens because, again, that's given to us in our formula up at the top here. And so 86 divided by 6 gives you roughly 14 units per hydrogen. And so then you look at each signal. So 57, the signal that integrates to 57, the triplet, divided by 14 is roughly 4 hydrogens. And then the quintet with an integration of 29, 29 divided by 14 is roughly 2 hydrogens. And so the triplet accounts for 4 hydrogens. The quintet accounts for 2 hydrogens. The third thing to look at is the splitting patterns of these 2 signals. So if you remember the n+1 rule, so n+1 tells us that if a proton has n neighbors, n neighboring protons, it's going to give us n+1 splitting in the signal. So for example, we look at our triplet and we can say there are 3 signals in this triplet, and so it has 2 neighbors. 2 would be n, 2 plus 1 is 3, and it's a triplet. So we know that it has 2 neighbors. It's split by 2 neighboring protons. Similarly, we can say that the quintet is split by 4 neighboring protons. And so when you evaluate all of these pieces of information as a whole, looking at the formula and then looking at, well, we have 2 signals. One accounts for 4 protons, one accounts for 2 protons. We have a triplet and a quintet. And the only conclusion that you can really draw is that the molecule that we're looking for is this molecule down here, where a chlorine has added to each of the terminal carbons in propane. And so this molecule is consistent with the NMR that we were given. But also, as you get better, you should be able to look at an NMR like this right off the bat and say, well, I have a 3-carbon molecule. Right, so our starting material has a plane of symmetry. I'm actually going to go ahead and draw it in. So our starting material has a plane of symmetry here, right? So if we draw a line through that central carbon, there's, you could say a carbon and a half on each side. And then when we look at the NMR of our product, we see that there are only 2 signals. So there's no other way to add 2 chlorines to this propane molecule that's not going to give rise to 3 signals instead. So again, we have to maintain that line of symmetry in the product. And we know that because there are only 2 signals, right? And so there's our line of symmetry in the product. And so we have 1 signal that accounts for the 2 hydrogens, one signal that accounts for these 4 hydrogens here and here, because they're equivalent, right? So all 4 of them give rise to a single signal. And that's our triplet. And it's because each of these protons has two neighbors. And the two neighboring protons are the two protons here on the central carbon. And so those two protons also give rise to one signal, and they give rise to the quintet because these two protons have four neighbors: one, two, three, four. Um, and so you should again, as you get better, you should be able to look at this NMR and say, well, there are only two signals. I have this three carbon molecule, so it has to be symmetrical, because we have to have two and only two types of protons in this molecule. Because remember, if we had a third type of proton, we would see a third signal. And so that is, I guess, two different ways to approach solving this problem. And that is the answer to chapter 15, number 78.